write explicitly some exercises in these notes. I don't know if you're doing the exercises. I hope that you're doing the exercises. I didn't write this exercise in on the notes, but I will. So basically, the exercises of last week. No, they were not from Logan. You can train a bit with the book of Logan. I can put the this chapter on my, and there's plenty of exercises at the end of any section. I'm not doing all the sections. Actually, I decided to follow the book of Logan mainly because the other one seemed to be a bit more advanced. But it's not more advanced. It's for a different kind of audience. So it's for mathematicians basically. The other book, the one of Bellomo. So it's clear that they have a different background from you guys. So I decided to follow instead the one by Logan, which instead is more. It's a book which is more. It's better for students of engineering. What's here? The only thing is that again, I cannot put the book online for the.
I found the Strongats book.
I found the Strogats. That's good. Salek. Yeah. Not that least. Not when we're online. So, but bad. Counseling. So, and let me know for anything for the Logan book. Try the Logan book. All right. In any case, there are some of these exercises. I can put also the pages, just the pages of the exercises on online in such a way that you can at least have a look to these exercises because are again good to train. So yesterday we arrived to the. Okay, we were introducing perturbation methods. What we did. See? Yesterday we were introducing perturbation methods. So we have introduced regular perturbation method. Just a very quick reminder. The idea, this is the more naive way of finding a perturbed solution to your problem. So usually regular perturbation method, as we said yesterday, yes, it works, but works rarely. So there are very, very simple problems where you can use the regular perturbation methods, but in most cases, this method fails. We have solved yesterday a couple of algebraic equations with the regular perturbation method. We have solved ODE with the regular perturbation method, but then we started to see some problem when, I anticipated that there were some problem with some of these. In particular, what we were looking at yesterday was the equation of the equation that let me write directly in the dimensionless, the non-dimensional form, which was this equation here. Where is it? Here. It's u prime equal to minus u minus epsilon.
Sir?
Yes.
Sorry, please share your screen. Thank you.
You are very correct. Thank you very much.
You're welcome. Sorry.
No, it's okay.
Sure.
There's always something that I'm forgetting in this thing online.
That's great. Thank you.
Okay, thank you very much. So we were saying that yesterday we arrived at this equation here, which, if you remember, this is the equation that you get when you are studying a mass spring system with a nonlinear term. So mass, which is attached to some spring, would have some hook force, which is putting a spring, which is pushing the mass in the equilibrium position of the spring. We were studying the case in which there is a nonlinear term, in particular term which is in the displacement to the power 3, so some power 3, and we did the exercise of make the equation dimensionless, and what we get is this equation here. This equation, we say that is the Duffing equation. Duffing equation. Well, here there are some things that are missing because I didn't write the initial conditions. The initial conditions we have calculated. I don't know if we calculated yesterday the initial condition as well or not, but the initial conditions are u not equal to 1 and u prime. Is it prime? Okay, I'm using dot instead of prime, so. Just for not confused with my notation, let me write this as u double dot. Well, this is some derivative with respect to some time. So u dot in 0 is equal to 0. So basically this is u not equal to 1 is telling me what is the position of the body when the dynamics of the system is starting, and u dot in 0 equal to 0 just tells me that when the mass is starting the movement, well, it started at still. Of course, I'm just putting the mass here down, and then I'm leaving, and this starts to oscillate. But the beginning, the velocity is 0. Okay, so I'm repeating this thing because I would like to show you one technique which is important that I didn't show you this yesterday. So the idea is that let me anticipate, regular perturbation method for this case is not working. So let's try some solution written as u of t equal to u naught plus epsilon u1 plus epsilon squared u2 plus higher order terms. So if you remember, this was, you can sneeze your nose, don't worry, you are allowed. Ti puoi soffiare il naso, che la nascosta. So if you remember, this is basically the ansatz that we, typical ansatz that we use for the regular perturbation method. So we make these ansatz for our solution, and then we say, okay, that's fine, let's take the ansatz, let's put the ansatz inside the equation, and let's solve term by term, order by order in epsilon, the equations, the system of equations that I found. When I found these solutions for u0, u1, u2, then in principle I should be able to reconstruct the approximated solution ut for every order epsilon that I like. Okay, that's fine. The point is that in this case, unfortunately, this method is not working. Let's see what happened in this case. If I'm putting this ansatz in my equation in this case, what I should have? Let me write in terms, well, let me put directly these things here inside. So what I will have is u double dot 0 plus epsilon u double dot 1 plus, well, let me stop to the first term, okay, because I will use just the first two terms in order to show you that this thing does not work. This is equal to minus u, so I have to substitute to u this u0 minus epsilon u1 minus higher order terms. And then I have minus epsilon times u to the power 3. What's u to the power 3? It's u0 plus epsilon u1 plus blah blah blah, everything to the power 3. Okay, now let's evaluate the zero order and the first order in epsilon. The zero order in epsilon gives me u double, no. Just a second. Here it's, I don't know why at certain point there are things that disappear. So we're saying that at zero order in epsilon we have u double naught, u double dot naught. This is oh come on. This is first order in epsilon. This is zero order in epsilon. So u double naught equal to minus u naught. And there is nothing else zero order in epsilon, right? Let's see first order in epsilon. First order in epsilon, I have u1 double dot, then I have equal to minus u1 here on the right hand side, and then I have the terms that is coming from here, which is minus u naught to the power 3. This one over 3. Right? All the other terms are higher order in epsilon, because this would give me something like epsilon to the cube, u1 to the cube, times epsilon, which is giving some epsilon to the fourth, and so forth and so on. And also cross terms, so terms which are multiplying, for example, u0 with some powers of u1, are always going to have some power in epsilon which is higher than 1. So let me discard these terms. I'm just considering first zero order in epsilon and first order in epsilon on these two equations. Now, what about the first equation? The first equation is well, there are also I should consider also the initial condition. Now, for the initial conditions, basically what I have is that u0 is u0 naught plus epsilon u1 naught plus blah 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 equal to 1. What about derivative is u0 dot in 0 plus epsilon u1 dot in 0 plus blah 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 equal to 0. Again, the idea is that you are still considering the same order in epsilon. So what are the initial conditions for the first equation? Question for you. What are the initial conditions for the first equation? So it's u0 0. Double dot is not possible because I cannot put u0 0 equal to 1. U dot, no, u0 dot. U0 dot. This is the second one for this equation. So this equation, it's a second order equation. So it means that I need two initial conditions. One is the initial condition for the function u of t in 0, and the second is the initial condition for the velocity. So what I need here is u dot 0 in 0, which I can read from here is equal to 0. All right. What about the initial conditions of the second equation, the equation from U1?
U1 is 0.
U1 is 0. Very good. U1 in 0 is equal to 0 because there is no term of order epsilon on the right hand side of this condition, and well, u dot 1, I think, as you probably now know, is u1 dot in 0 is equal to 0, which is coming from this second condition. Okay, fair enough. So we have to solve these two problems. The first problem is relatively easy. So, what's the general solution of this equation of this second order differential equation? Do you remember how can I write the solution of this equation? Sum of what?
Of the general solution. It's no, it's not.
Buon tentativo. However, here this is a homogeneous equation. Okay, so the homogeneous. This is in any case some homogeneous equation which appears millions of times in mathematics, in physics, in biology, in engineering, and everything. So remember that that's actually exactly like the case of first order differential equations that we solved many times during these weeks, whose solution is an exponential. In this case, the solution is always something which is like the sum of sine and cosine. So basically, this thing is something which is going like a cosine of t plus b sine of t. Actually, this thing should be, this is just the general solution, but with the constants. We have to determine the constant. How do we determine the constant? We determine the constant using the our initial conditions. So if I'm imposing the initial conditions, the first initial condition tells me that u naught in 0 must be equal to 1, this one. So let me assume that u naught in 0 equal to 1. This means that I have to consider t equal to 0. So cosine of 0 is 1. So this is a times 1 is 1. Plus b of sine of 0, which is sine of 0. What's the sine of 0? 0. So the first, when I'm considering u naught in 0, this is just a. But the initial condition tells me that this must be equal to 1. So the first initial condition tells me that a must be equal to 1. Great. Second initial condition, the condition on the velocity, this one. What's the derivative of the cosine?
Minus.
Very good. So u dot 0 t is equal to minus a times sine t. What's the derivative of sine? Plus b cosine of t. Now let's calculate this quantity in t equal to 0. Sine of 0 is 0, so this term is not here. B times the cosine of 0 is B. So this is B. But the second initial condition, which is this equation here, tells me that this quantity must be equal to 0. So the second initial condition tells me that B, capital B, must be equal to 0. So B equal to 0, A, capital A equal to 1. Finally, I can write the function u naught t, the general solution of this problem, this ODE plus these two initial conditions. And the general solution, the solution which is fulfilling respect this initial condition is u naught of t equal to cosine of t. Is it clear? Pubblico da casa, you guys there at home, everything is clear?
Yes, Professor, but
Yes,
I
Peter.
can understand about the initial condition that you solve a little.
Okay.
That when you about the initial condition that you wrote the formula, I can understand.
Why I wrote this formula?
I mean, u dot equals minus u dot that you wrote the initial condition.
So you mean these ones here?
No.
No.
The middle of the page.
The immediately after is these ones?
Yes. Yes.
Okay.
Yes.
Okay, so these ones comes from these ones. So the right. So the do you understand these ones instead? The fact that I'm just rewriting u0
Yes, Prof.
equal to 1 in this way and u dot in 0 equal to 0 in this way. Okay?
Yes. Okay.
Fantastic. Now what I'm doing is just to consider the corresponding order in epsilon of these equations. So this equation here, the one for u double dot, u0 double dot, is the equation corresponding to the order 0 in epsilon. So the corresponding initial conditions must be the initial conditions of order 0 in epsilon. What are the initial conditions here? What are the order 0 in epsilon in these conditions? So in the first equation, order 0 in epsilon, there is just this term here and this term here on the right hand side. So the order 0 in epsilon of the initial condition is u naught in 0 equal to 1. And for the second initial condition is, again, I have to consider only the order 0 in epsilon. It's u0 dot in 0 equal to 0. And that's what I wrote here on this side of this equation. Then I wrote the equation for which is first order in epsilon. So I'm looking for all the terms in my equations which are first order in epsilon. In the equation, this gives me u1 double dot equal to, well, this expression here. On the other hand, I have also to identify what are the terms in the initial conditions which are first order in epsilon. What are the terms which are first order in epsilon? There is just this one. This one tells me that is u1 evaluated in 0 must be equal to 0 because this is equivalent to this thing here. Right?
Yes, Prof.
And the other initial condition tells me that u1 dot in 0 must be equal to, again, 0. So that's actually what I wrote here on this side, corresponding to the equation for u1.
Yes, Professor. Thank you.
Great, fantastic. So, all right, in any case, the first equation with these initial conditions is solved by this function, u naught of t equal to cosine of t. Now, what I have to do is to go into the second equation and use this cosine of t. So the second equation, second problem, initial value problem is u1 double dot equal to minus u1 minus cosine of t cube, because it's u0 cube. Correct? It's this term here. And this must satisfy the initial condition u1 in 0 equal to 0 and u1 dot in 0 equal to 0. It's your moment. How do you solve this equation?
The sum of the general solution of the homogeneous equation and the particular solution of the homogeneous equation.
Exactly. So the solution of this equation is a second order differential equation, a non-homogeneous second order differential equation. It's non-homogeneous because there is this extra term here. There is a term in minus cosine cube of t, cosine t cube. Well, the cube of cosine of t. So the solution of this thing is going to be the sum of the general solution of capital U double dot equal to minus capital U plus a particular solution of the entire equation. Now, what is the solution of this, of capital U double dot equal to minus U? Why? That's the same equation that we have solved, but this equation here is cos t because we imposed the initial conditions. Here I'm not imposing any initial conditions yet. So what I have to do is to find the general solution, which is some capital U equal to, let me call A tilde. A tilde cosine of t plus some B tilde sine of t. So this is the general solution of the associated homogeneous equation. Great, fantastic. The big problem now is going to be to find the particular solution, so the special solution for the non-homogeneous equation. It's in the appendix of the notes, again, of the notes of this week. So the idea is that you can use, again, the technique of variation of parameters, which is a technique which is a bit boring because it's some kind of longer, trivial but longer calculation, cumbersome, complicated, but I mean it's trivial calculation. It's just integrals that you have to do. What's the idea? The idea is that I can consider some function sigma, capital sigma, that looks like this thing here, just looks like this, but where A tilde and B tilde are substituted by functions. So basically, I'm considering a function sigma, which is like this: gamma 1 of t cosine of t plus gamma 2 of t sine of t. You see, it's very similar to the general solution of the associated homogeneous. But the difference is that instead of having this a tilde and b tilde, here a tilde and b tilde are constant. Instead here I'm imposing that there are some generic functions, gamma 1 and gamma 2. Now, here you can solve the problem in a completely generic way, but in order to simplify things, for this kind of problems, only for this kind of problems, so when we are solving this kind of equations, you can assume that gamma dot 1 cosine of t plus gamma dot 2 sine of t is equal to 0. Now, this is can probably looks like a mambo jumbo, una magia. That's actually I'm assuming this because this is what is simplifying later the equations. In principle, if I do not assume this thing, what I should do is to take this sigma, to put the sigma into the non-homogeneous equation, and try to find a match between gammas and the non-homogeneous term. Now, this will have some degrees of freedom. What I'm doing in order to constrain these degrees of freedom to not to have too many things to find is to assume that this is true, because this way I will simplify something that comes from putting this sigma in this equation. In fact, if I'm assuming this thing here, when I put sigma into the non-homogeneous equation, the condition that I found is this one: sine of t plus gamma dot 2 sine t equal to minus 1/4 3 cosine t plus cosine 3t. Questions for you. Where does this term come from? It's exactly cosine t to the cube. It's just another way to write. This is just an identity. You are not supposed to know by heart and memoria all these identities. Okay? Just remember that sometimes you have to simplify sine and cosine, because otherwise then the integrals that are coming later are a bit difficult to be solved. So basically, this is just a way to rewrite the terms here on the right hand side, minus cosine t to the cube. All right. So what you have to do is to solve this system. If you solve this system, you will get gamma 1 and gamma 2. If you get gamma 1 and gamma 2, you get the particular solution of the non-homogeneous equation. If you get the particular solution of the non-homogeneous equation, you have the general solution of non-homogeneous, because you can consider the sum with the general solution of the associated homogeneous. just for the chronicles. What are the solution? Let me write here the solution. You can check it then later at home. Gamma 1 is minus 1/4 cosine t to the power 4, and gamma 2 is minus 3/8t minus 1/4 sine 2t minus 1/32 sine 4t. But these are not very important, but it's probably it's useful if you check this formula at home. So if I have gamma 1 and gamma 2, what I can do now is to write the general solution of this equation here. And the general solution, as your colleague was saying, is some u1 of t, which is the sum of the general solution of the associated homogeneous, c1 cosine of t plus c2 sine of t, plus the particular solution, so plus sigma. What is sigma? Sigma is gamma 1, so it's minus 1/4 cosine of t to the power 4 times cosine of t. Correct? That's correct. And then I have gamma 2 times sine of t. So gamma 2, what is gamma 2? Gamma 2 is written here. It's minus 3/8t minus 1/4 sine of 2t minus 1/32 sine of 4t. Everything multiplies sine of t. Very good. Complicated expression. Yes.
Sorry, but the last sentence that you wrote, the second one is close. I mean, that's C1 cosinus t plus C2 sinus t plus. That's in the second one plus.
No, this one is a minus. So basically it should be plus, open parentheses, minus this thing, because it's this is gamma 1 and this is gamma 2. What I'm writing is plus gamma 1 cosine t plus gamma 2 sine t. But gamma 1 is minus 1/4 of this thing. Good. So, all right, this is the general solution, still not the solution of my initial value problem, because now what I have to do is to impose the initial conditions. The initial conditions are these, the initial conditions, what are the initial conditions? Are u1 in 0 equal to 0 and u1 dot in 0 u1 dot in 0 equal to 0. So I have to impose these two conditions, which basically means that I have to evaluate this expression in t equal to 0 in order to fulfill the first initial condition. And then I have to take the derivative and evaluate in 0 to fulfill the second initial condition. That's algebra. I can say this part. Again, that's something that probably is good if you are checking at home, even if I know that nobody is checking this at home. What you will find, if you do that, is C1 equal to 1/4 and C2 equal to 0. Put everything together, check the combination. What you find is finally the solution for the initial value problem for u1, which is cosine 3t divided by 32 minus cosine of t divided by 32 minus 3 over 8 times t sine of t. And here we have the problem that we were commenting yesterday. So what is the problem? The problem is that now let me write my approximation of the solution. So ut. The very initial problem was to find this ut that I approximated with the u0 of t plus epsilon u1 of t, etc., etc. Now u of t is equal to what? u0, and u0 it's cosine of t. Fantastic. u0 cosine, it's cosine. And then I have plus epsilon times u1 of t. What's u1 of t? u1 of t is all this beast which is here. So cosine 3t over 32 minus cosine of t over 32 minus 3 over 8 t sine t plus higher order term. So now, if you remember, what was the problem that we were anticipating yesterday? The problem that we were anticipating yesterday was due to this term here, what we call the secular term. Why it is a problem? It is a problem because t, it's a time. So in principle is unbounded from above. So basically this means that t can be everything between 0 and infinity. I don't know what's the notation that you're using. Sometimes you find this notation, sometimes you find this notation. I don't know what you are using. This one, all right. So this means that wherever it's epsilon, epsilon can be small as much as you want. But since here there is a term which is going like epsilon time t, and t is unlimited, I can arrive to infinity, then these terms at a certain point can become important, can become large. If this term becomes large, this means that this is not anymore an approximation. This term is a big term, and I cannot consider this one as an approximation of the leading order term. Actually, this kind of approximation is an approximation that it works up to a certain point, in the sense that you can always say, I'm not taking t, which can arrive, I'm not studying dynamics from 0 to infinity. I'm just considering an amount of time between 0 and t, capital T. Then if I'm choosing with 0 and capital T, I can choose epsilon in such a way that this term is small, and I'm fine. But this works only if I'm considering a limited amount of time. If I'm going inside, if I'm considering instead all the way from 0, or for time from 0 to infinity, well, the approximation loses validity. There is an alternative, actually there is a trick for dealing with this kind of equations, and that's actually the trick that we are showing now. Yes, I'm doing this, and then we will stop. Also because this is taking a bit of time. The alternative is what is called the Poincaré-Lindstedt method. Yeah, that Poincaré. I mean, Poincaré has done basically everything in maths. I don't know if he used to have any. If he was a fan. I don't think that Poincaré was a fan. I mean, there are some famous families of mathematicians. Their names, for example, Bernoulli. You have seen probably tons of times Bernoulli, but Bernoulli was a family. I mean, you have to take into account who of the Bernoulli family did what. Gauss was a family. No, Gauss was not a family. Gauss is the Gauss. Yeah, yeah. Actually, recently I discovered, this is another parenthesis. I told you that there was this student of mine doing a work on, a thesis on dunes. And one of the most important scientists, mathematician, working on these dunes is a guy whose name is Albert Einstein. I didn't know that this guy was actually the son of Albert Einstein. So there are pictures of him with his father, and this is one of the most important scientists that worked in the theory of dunes, of our models of dunes. Okay, close the parenthesis. Poincaré-Lindstedt method. È una cosa che non c'entra niente, te lo fa. So, what can we do here? What we can do is to introduce a, that's why it's a trick, distorted time scale. So I can consider a time which is not the time of the equation that we solved here. I'm considering a time tau, which I write as omega times t, which is equal to I can expand this omega in such a way that is like perturbed in epsilon. So this is well, omega 0 plus epsilon omega 1 plus epsilon squared omega 2 times t. This is the most generic one. In any case, what I will do is to assume that omega 0 is equal to 1 and always do a transformation in such a way that this is true. 1. I mean, this way the first order term would be exactly t, which would reduce me to the problem of before. So what I'm doing, what I'm trying to do now is to reabsorb the problem given by epsilon t into the time. Because I have no problem in having a time which is increasing up to infinity. The problem is not in the time. The problem is in this, if this infinity arises in this quantity here. If the infinity arises in time, well, that's fine. That's just another way for saying that I'm looking for time which is going from 0 to infinity. Who cares?
The problem is the product between epsilon and time.
Yes, the problem is the product is on epsilon and time, which appears in this solution here inside. If it appears here inside, this means that this is not an approximation. And if it's not an approximation, because an approximation means that this term is small. If this term is not small, it's not an approximation. If this is not approximation, everything falls down. So what I'm doing is just to reabsorb this infinity that's put in this way in time, defining this kind of time. So let's see what happens then in this case. What I have to do is to recast, to reformulate Duffing equation in terms of tau. So how this will work? Basically, tau is appearing. It's just a proportional to t. T is appearing in my Duffing equation only as the independent variable with respect to which I'm differentiating. So t appears as d squared u in d t squared, right? This is the u double dot term. What I can do is to multiply and divide by omega squared. So omega squared times dt squared is written here. It's basically d tau squared. You see? Tau is omega t. So if I'm differentiating both the sides, what I get is d tau equal to omega dt. And if I'm considering the tau squared, this is omega squared dt squared. So this terms here becomes omega squared times the derivative, the double derivative of u with respect to tau, which I will call u double prime. So remember, d in the t, for this problem, d in the t, it's like dot. D in the tau, it's, oh. In any case, then the tau is prime. It's freezed, guys. I can't go on. Yes. Non ci credo. I was saying that then the tau is prime and then the t is a dot. The right-hand side of the Duffing equation doesn't change because there is no time there. The right-hand side was minus u minus epsilon u to the power 3, which is still minus u minus epsilon u to the power 3. Initial conditions also basically do not change because the initial conditions were u0 equal to 1. The other initial condition? Questa? Sì. La derivata seconda rispetto a tau. So the initial condition was, the first initial condition was a u in 0 equal to 1. Fair enough, it's the same. The second initial condition is u dot in 0 equal to 0. In principle, I should multiply and divide by omega in order to, so the second initial condition was this one. What does this mean? This is the u in the t in 0, right? So in principle, what I have to do is to multiply and divide another time by omega. So this is the tau. This is omega u prime in 0 equal to 0. But omega u prime in 0 equal to 0 is u prime in 0 equal to 0. So now what I can do is finally to use again the regular perturbation method with this special time. So what I'm doing is to try to solve this equation, doing the ansatz, making the ansatz that u is equal to u0 plus epsilon u1 plus epsilon squared u2, etc. What do I get from this equation? So omega squared, omega is written here. Omega is 1 plus epsilon omega 1 plus other terms. Do I need the other terms? No. Squared. Then I have second derivative of u with respect to tau, which is u0 prime prime plus epsilon u1 prime prime plus epsilon squared u2 prime prime plus other orders. And this terminates the first term. Then I have this term minus u. So minus u gives me minus u naught plus epsilon u1 plus epsilon squared u2, blah, blah, blah. And then I have the last term, which is minus epsilon times u to the power 3. Let me write directly what are the terms that I need from the power, from u to the power 3, which is u naught q plus 3 epsilon u naught squared u1 plus higher orders in epsilon.
No, because why we don't use epsilon squared in the first
Here inside?
Yeah.
I will not need, actually I can also forget about this. I'm stopping to the first order.
Because of the starting
Yeah, that's possible. I mean, I can also write this here. Okay, that's fine. I can write it here. In reality, it's because I'm not using the later. But yeah, I can write it here. And then I have the initial conditions. The initial conditions, which are u evaluated in 0 equal to 1, which I can write as is this true with this kappa here? 0, 1, 2. No, well, I have a mistake in these notes, but nothing of very important. Do you understand this expression? That's actually the same thing that we have done in all the cases up to now. This is basically the sum of what? Epsilon to the power 0 times u0. So it's u0. evaluated in 0 plus epsilon to the power 1 u1 evaluated in 0 plus epsilon to the power 2 u2 evaluated in 0 plus blah 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 equal to 1. That's actually just another way for writing this expression. And this is instead another way for writing the expression for the initial conditions for the velocity. Now what happens? Now what happens is that we have to find the order by order the epsilon. We have to find the corresponding order of epsilon in the equations. So at first order, what do we have at first order? Sorry, at 0 order in epsilon, what do we have at 0 order in epsilon? 0 order in epsilon, come on guys, tell me what is the 0 order in epsilon of this equation? 1 0 prime prime minus u0 and full stop. There is just. So the 0 order is 1 times u0 prime prime 0 prime prime equal to minus u0. Well, actually, we have also the initial condition. So the initial condition is u with u0 in 0 equal to 1, and u dot 0 in 0 equal to 0.
1.
Huh? The 1 here is 1. It's 1 times u0. Here there is a multiplication.
Why you don't?
Sorry, it's u prime. Thank you. Because it's exactly where the sun is arrived. Yeah. And then what's the first order in epsilon? Tell me what I have to write. Omega 1? Eh? Omega 1 squared. But omega 1 squared from this one. This would be epsilon squared omega 1 squared. So this is not the first order.
Only U1, the second.
This one?
No.
This one?
Yes.
So. U1 prime prime, just U1 prime prime. I have many more here.
U1 prime prime goes in line with the other space.
So I'm multiplying. That's actually the point. The point is that I have to let me write this probably more explicitly. So this thing here is 1 plus twice epsilon omega 1 plus, well, high order terms, right? So when I'm multiplying this thing by this thing, I have two terms which are over. U not prime prime. I have 2 omega 1 U not prime prime. And I think that there is still one thing.
On the other side, the epsilon u1 prime.
Epsilon u1 prime prime is here. Actually, there is another thing that disappeared because of this object, because it was here. So there is this term which is minus u not q. It disappeared. I don't know why it is disappearing. I really don't understand. So let me rewrite then the equation in a more clear way.
But the first you wrote the last line, isn't it omega 1?
Which one? This one.
The first.
This one is without omega 1 because u double prime is multiplying 1.
Okay.
If I'm multiplying by this one, I would have epsilon squared.
Okay.
So yeah, let me rewrite more clearly. This is u1 prime prime plus 2 omega 1 u naught prime prime equal to minus u1 minus u naught q. That's exactly the same equation, just clear. With the initial condition, which are u1 0 equal to 0 and the u prime 1 0 equal to 0 as well. What is the solution of the first equation? Actually, this is exactly the same equation of before. So what is the solution?
The solution is cosine of t.
Yes.
Of tau.
Cosine of tau. What was the name? Tau? Yeah, tau. Tau. Cosine of tau. Yes. So the solution of this is u naught of tau equal to cosine of tau. So what I can do is to go to the second equation and to write the second equation using the fact that u0 is cosine of tau. So what I have is u1 prime prime. Let me put the minus u1 from the right hand side to the left hand side, so it's plus u1. And then I have minus u0 to the cube, which is minus cosine of tau cube. Then I have another term which is minus 2 omega 1 times the double derivative of u0 with respect to tau, which gives me a minus cosine. So here it's plus 2 omega 1 cosine tau. Correct? Correct. Which is very similar to what we have found before. You remember, before the Duffing equation, we found without the Poincaré-Lindstedt method, we found this equation here. Now, using the distorted time, we found this extra term here. Now, if we are using all the nice tables of sine and cosine that you can find on internet, on books, and wherever you want, what you can do is to transform this right-hand side in this way here. 2 omega 1 minus 3/4 cosine tau minus 1/4 cosine 3 tau. So these two are the ones that we got in the wrong expression before. You remember? Actually, it was cosine cube tau, and using all the trigonometric blah blah blah, you can rewrite in this way here. This is again the extra term that we get because we are considering the distorted time. So what is the advantage here? The advantage here is spoiler. The spoiler is that this cosine of tau is the term that is responsible of the secular term in the solution that we showed before. So what we have to do in order to regularize our solution is to kill this term. And we can do that because now we have this parameter omega 1. So what I can do is to choose omega 1 in order to kill this term. I can choose omega 1 in such a way that 2 omega 1 minus 3/4 is equal to 0. So I choose omega 1 equal to 3/8.
Okay. Sorry. How can cosine be a secular term?
The cosine, so this one was the one that once integrated was giving you the secular term. So this is the spoiler. See, yeah. So basically, I do not want to write down again all the solution, including this term. So I'm already telling you that the secular term that we described before comes from this cosine of tau. So if I kill this cosine of tau, I will not have the secular term. So in order for doing this, I have to choose omega 1, which is a parameter in my definition of distorted time, in such a way that this term is 0. And this term becomes 0 when omega 1 is equal to 3/8. This is just 2 omega 1 minus 3/4 equals 0, which solved gives me omega equal to 3/8. If I choose omega 1 equal to 3/8, I kill this term. So my equation now becomes just u1 prime prime plus u1 equal to minus 1/4 cosine of 3 tau. If you look, I'm not going to do the calculation. If you look for the solution of this problem with these conditions here, with these initial conditions here, u1 0 equal to 0 and u prime 1 0 equal to 0, if you look for this solution, you will find u1 equal to 1/32 times cosine 3 tau minus cosine of tau, which is basically the solution without the secular term, which was the problematic one. In such a way that I can finally write the solution of the entire problem as u tau, which is u0 plus epsilon u1. So u0 is cosine of tau plus epsilon, u1, which is this one, 1/52 cosine of 3 tau minus cosine of tau plus higher order terms. But I cannot forget that I have also to say that I have this distorted time, which was omega time t, that is 1 plus epsilon omega 1 plus, well, higher order terms times t. And this I can write as, sorry, t plus 3 over 8 epsilon t plus other terms. So if I do a transformation which send me the usual time in this distorted time tau, I find a solution which is a well-behaved solution, a solution without the secular term, and I'm fine. Pausa.
Ultimi 10 minuti di pausa, sì.
Va bene.
It's break.
It's. Say it again.
Break.
It's breaking.
Pause. Pausa.
Yeah. I
Ah,
said
okay, okay.
Yeah.
Okay. Okay.
Yeah.
Thank you, Sid.
Yeah. Say it again.
Professor, I'm sorry, I have a question. If you can answer me.
Yeah.
I'm sorry, because you want to harass. I'm sorry. Professor, some of the equation and some of the problems of this course I can't understand, and I can't do what should I do for my problem. Sometimes I am very nervous about this.
That you cannot understand the equation or you cannot understand the problems.
I cannot understand the procedure of the method of this course. For example, about some of the equation, I can't understand what's the procedure and what is happened. Something like I should write and take notes, but after that, when I review, I can't understand again, and I'm so nervous about this.
All right, but is this is the level of mathematics too high? Is there anything that you didn't recognize as a mathematical object?
Yes, I can understand something, but for example, this section,
Yeah.
uh, mm, the end of the class, I can't understand anything.
All right. Are you studying also from the books that I suggested you?
Yes, yes, I found it and I read it.
The book of Logan or
It
the other one?
yes, no, the book that you told us the previous section
This one, look, because this is
is
important.
applied mathematics.
Yeah, applied mathematics.
Yes.
So you're and can you follow this book? Can you understand the book? Because basically, what I'm doing is just to explain what is in this book.
Yes, but about the books, some parts of the books is very, it's not clear for me, and some of the sometimes I cannot understand it again.
Okay, I see, but I mean, I'm here for this reason. If you want, whenever you have something that you do not understand, write me an email, and I'm available to talk outside of the class. I mean, I'm available twice per week for a couple of hours. So if you need help, you can say, "Look, I have a problem with this part. Can you explain me again how do I do this part?" And I will do that.
Yes, Professor, you are available. Previous, I sent you emails and thank you so much because you answered me. And I'm ashamed because most of the time I should send email to you, and it's a little a little not good to send everything to you and ask you again and again.
Look, we are here for this reason. I mean, you are paying taxes. Since you are paying taxes, you are paying me with these taxes, and I'm offering a service. So it's there is no shame in writing questions, and on the contrary, I invite you to ask as many questions as possible, and I will have all the I will be very happy to answer to all these questions. It's important that you understand. I can understand that at the beginning probably these things seems a bit could seems a bit complicated. But if I don't know where you have problems, I cannot help.
Mm-hmm.
I don't know if you have problems, for example, with the differential equations. Because if you have problems with solving elementary differential equations, there is actually one chapter in the book that I didn't consider at all because it was some simple, some chapter that I thought that students know. But if you have problem with the chapter, then I can understand that it's complicated the rest of the course. So we can discuss that chapter on simple solutions of ordinary differential equations. Believe me, then it's just a matter of logic. What is more important is you can train with the exercises that you find on the book of Logan. There are a lot of exercises. So
Yes, yes. In the
it would be good to try to do those exercises because well, there are some of them that are simple, other ones that are more complicated. But if you do and redo those ones, then probably you will understand what's the technique. Then it's just a matter of understanding what kind of technique you have to use. For example, the Poincaré instead method is a method that it's important from the theoretical point of view, but from the practical point of view, it's something that you don't use a lot. Actually, the kind of method that we use more from the practical point of view are some methods which are arriving later. And but if you do not train on these things, well, again, I cannot say I cannot enter and help you where you need. So what I need from your side is, first of all, send me an email anytime that you have some difficulties, even if it's just 1+1, no problem. I mean, we are here to discuss even 1+1. And second, do as many exercises as possible.
Yes, professor. That's right. I should practice more and more, and I will send you an email if I have a question. Thank you so much, professor. Thank you.
Thank you, sir.
Okay. Look, in principle, this part is easier. In principle, just definitions, a bunch of definitions. So the idea, what we want to understand now is if there is any technique that allows me to see if I can find an approximated solution to some problem. Okay, so I would like to have some axiomatic idea. I want to have some scheme that allows me to say, look, if I'm taking this problem and looking to an approximated solution to this problem, I can do that because of this, and this. Okay, so what we want to do then is what is called asymptotic analysis. Now, let me introduce some basic definition to analyze these approximate solutions. So let me suppose that I have two functions f and g of epsilon, which are defined in some neighborhood of epsilon equal to 0. So these are defined close to epsilon equal to 0. Now, we say that f of epsilon is a little o of g of epsilon, is a little and little o of g of epsilon as epsilon goes to 0, if the limit for epsilon that goes to 0 of the absolute value, the modulus of f of epsilon divided by g of epsilon is equal to 0. Then we say that f of epsilon is a big O of g of epsilon as epsilon go to 0 if there exists a number, capital M is a number, such that the absolute value of f of epsilon is bounded by m times the absolute value of g of epsilon. So g is what usually is defined to be a gauge function. Usually g of epsilon, actually, g of epsilon. This is a kind of function with the respect to which you are comparing your function f to understand what's the order of f. For example, if I say that f is a small o of 1, what does this mean?
Can you repeat it? Gauge function?
The gauge function. Gauge function is the way you are referring to this g of epsilon. It's just g of epsilon. G of epsilon. So a g of epsilon is usually said to be a gauge function. È una funzione rispetto alla quale ti stai riferendo per poter trovare qual è l'ordine di f di epsilon. Usually this g of epsilon is some power of epsilon to the power n, or some power of epsilon times log, epsilon n2 times log, blah, blah, blah. And what you're doing is to compare f of epsilon to this gauge function. So again, what does it mean that f of epsilon is a small o of 1? If I'm using this definition here upstairs. So technically the definition for this small o, this one, right? What I'm saying is that f of epsilon is equal to a small o of a function which is equal to 1. G epsilon in this case is 1.
It means the limit of 0, absolute value, the ratio of epsilon over 1.
Yes, and what is the ratio between f epsilon and 1? Yes, that's actually, this is telling you that the modulus of f of absolute value of f of epsilon, the limit of the absolute value of f of epsilon is equal to 0. And what if I say that f epsilon is a big O of 1?
F epsilon is absolute value, it's little, smaller or equal than 1.
No, to m. So basically this means that f epsilon is bounded. F epsilon is constrained to be in, since this is the absolute value, this means that if m is this number which is positive, f of epsilon must move between m and minus m. Must stay here inside. So this means, what happens here? This means that f epsilon is bounded in some neighborhood of 0. Okay, let's see some examples of this equation. These are definitions again. We are still not in the application part. These are mostly definitions that we have to use for arriving to some application.
Sorry,
Yes.
Professor. What is right in the last sentence?
Yeah, this one, no?
Yes. This.
Yeah, it is f of epsilon is
Yes.
bounded in a neighborhood of 0. Neighborhood. Nella vicinanza, intorno, grazie.
Okay. Thank you.
Now, what we can do is to, well, this is just simple exercise. I will do just one of them. So let's, for example, verify that epsilon squared log epsilon is a little of epsilon as epsilon goes to 0 from the right. So what do I have to do to verify this thing? What do I have to calculate? I have to calculate the limit for epsilon that goes to 0 from the right. 0 from the right because the log is not defined in the negative epsilon. Of what? Of my function, f of epsilon in this case is epsilon squared times log epsilon. Epsilon squared log epsilon divided by the g of epsilon, which is in this case just epsilon. So what I have to do is to find the limit for epsilon that goes to 0 plus of epsilon log epsilon. What is this limit?
0 not to 1.
That's it's 0. Non ho capito che hai detto sinceramente.
No, è 0 per 1.
Ah! Però perché hai detto per 1? 0 per 1?
0.
Perché 0 per 1?
All'NT epsilon 0 a 1.
Il logaritmo di 0 quanto è?
No,
Quanto è il logaritmo di 0?
infinito.
Minus infinito. So actually this is 0 because it's well, this is a you can calculate this limit with the theorem of the L'Hopital. So what you can do is the following. Ripetetevi i limiti. This is the limit of for epsilon that goes to 0 of let me write this as log epsilon divided by 1 over epsilon. This is the same thing, right? And now what I can do is to use the rule of the L'Hopital, which tells me that this limit is equal to the limit of the derivatives of the numerator and the denominator, if this is finite. So what is the derivative of the numerator? It's 1 over epsilon. This is the limit for epsilon equals to 0 of limit the derivative of this, which is 1 over epsilon. The derivative of 1 over epsilon is minus 1 over epsilon squared. And this gives you the limit for epsilon that goes to 0 of minus epsilon. This is 0. Okay, in any case, this means that yes, epsilon squared log epsilon is a little o of epsilon. Now, why do I need all these the definition? This definition is something that I need to, in order to define what is an allowable error for my problem. So what I want to understand is what I want to do is to define how big can be the error of my solution in order to say that the approximated solution is still a good solution for my problem. And I will use these concepts, this definition, for doing this for clarifying this point. Now, I need another definition, which is the following. So I will say that some approximation y alpha of t and epsilon is a uniformly valid approximated asymptotic approximation, sorry. Asymptotic approximation of the function y of t of epsilon on some interval I as epsilon goes to 0 if the error capital E of t and epsilon, capital T, yeah, which is basically defined as the difference between the exact function, so y of t and epsilon, minus the approximation, y alpha. So if this converges to 0 as epsilon goes to 0 uniformly, I'm commenting now, okay? So what I'm saying here is that imagine that I have some function which is this y of t and epsilon, this function here, okay? I can say that another function y of with alpha of t and epsilon is a uniformly valid asymptotic approximation of y if the difference between the two functions goes to 0 uniformly as epsilon goes to 0. Uniformly means not just in a point, but in on some interval, in some neighborhood. Okay, so basically what I'm saying is that what I need to do, as you can imagine, is that I have to minimize the error. I have to understand how can I say that this error, this difference between the true function and the approximated function, when this difference is small. When this difference is small, if I'm able to give a a list of rules for saying this error is small, then I would say that, okay, that's fine. This y alpha is a good approximation for my function y. So for example, let me consider this the following example, because possibly it's going to be easier. Let me consider the function y of t of epsilon defined as e of minus t epsilon, where t is larger than 0 and epsilon is much smaller than 1. And let me test what I've said with some Taylor truncation of y. So my approximated function, in order because I want to test to understand how things are going, is going to be just the Taylor expansion up to 1, 2, 3, up to the third term, first three Taylor terms of e exponential of minus t epsilon. I will not ask you what are the first three terms of the Taylor expansion. So what I have to do is now to test if to test the error of y alpha with respect to y. So I have to define this quantity which is given by y of t epsilon minus y alpha t epsilon. What is this quantity? Actually, this quantity, well, this is e to the minus t epsilon minus these three terms here. This is basically, no, that's the rest of the Taylor expansion. Because if I'm Taylor expanding and I'm continuing here in writing the 1 over 3 factorial t cube epsilon cube plus 1 over 4 factorial blah 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 t4 epsilon 4, etc. So when I'm doing this minus this, basically what I get is all these terms which are here. There's minus 1 here. So this is going to be minus 1 over 6 t cube epsilon cube plus, well, whatever, either higher order terms. What is this thing? This thing, we say that is the error E, no? And what I can say of this error is that this is a big O of epsilon cube. For a fixed time t. So basically for a fixed time t, this quantity is bounded by t cube over 6. Well, otherwise I can use another definition. I can say that this is a big O of epsilon squared because the limit for epsilon that goes to 0 of the error divided by epsilon squared goes to 0 as well. So it's bounded. So this kind of definition is it's kind of easy to check if I have functions. Because if I have a function, what I can do is exactly what I've done now. I can write the Taylor expansion of the function and decide to stop to some term of the Taylor expansion and then compare the errors and okay, it's okay. Or I can define another function which can be an approximant of the function and then comparing the error and see if this is if this is some quantity which is limited or not. Now, yeah.
But why we don't have done the limit for epsilon 0, like the definition? The last definition.
This one? This one?
No, scusa sotto l'ultimo.
L'ultima proprio. Sì, è quello che dicevo, che puoi metterlo come un O grande di epsilon squared. O grande di epsilon squared, che cosa significa? Che sto prendendo limite per epsilon, cioè questo deve essere bounded. L'errore, so the error is something which is proportional to t to the cube, e to the cube, right? Is this quantity here. Saying that this is a big O of epsilon squared means that I'm considering this thing here, right? Now, if I take the limit for epsilon that goes to 0 of this thing here, this goes to 0. What's the point? The point is that this error does not converge uniformly to 0. That's actually why I was not taking into account the limit also for epsilon is equal to 0. This converges to 0 only when t is fixed. Questo è lo stesso problema del secular term. This is actually the same thing that happens with the secular terms because there is if I fix t, fine. If I don't fix t and I fix epsilon, I can always find a t which is large enough for saying that this error is not small, it's some large there, which basically means that this approximation is not good. If the error is large, the approximation is not good. So the point is that, again, for functions, this is relatively easy. Because for functions, you have a function, and you can have another function, and you want to compare the two things. So what you do is take the difference between the two functions, study how this difference goes when epsilon goes to 0. Fair. Something relatively complicated. The problem is when you have instead differential equations. So we need some definition to understand how well an approximated solution is approximating the exact solution of a differential equation. So we say that now I'm saying that y alpha of t of epsilon, that's the same notation, but okay. We say that this satisfies the differential equation f of t y nothing y prime y double prime epsilon equal to 0, again on I and as epsilon goes to 0. If this quantity, which is called the residual error, and which is defined as f of t y alpha y y dot alpha y double dot alpha epsilon goes to 0 uniformly as epsilon goes to 0. A second, write down this thing and I will comment the meaning. Differential equation. Differential equation.
The second line, if alpha of
If-
alpha of the epsilon.
If R. So this is no, you are writing. Write down.
meantime, I have a question about the things that we have done before.
Yeah.
The epsilon alpha, sorry, y alpha,
Yeah.
so is equal to the entire Taylor series.
No, no, no. Y alpha was just this. I was approximating with these three terms.
But if you approximate only with those three terms and you substitute in the error, and you do the limit, it doesn't tend to 1.
No, because you cancel 1. I mean, you have this function minus the three terms,
Yeah.
right? So this function here,
Tends to 0.
no, this function here is 1 minus the epsilon plus 1/2 minus 1 over 6 plus 1/4, etc., etc. That's why actually I wrote this thing. This is exactly the Taylor expansion of e to the minus t epsilon. So now I'm subtracting to the entire function the first three terms. What do I have is the rest of the Taylor series, which is this minus 1/6 t cube plus other terms. Now let me comment instead this definition that I gave. So this is somehow to use the same idea of error but connected to the differential equation. If you remember before, what we have done is to define what is this here. So we have defined some approximating function as that function which allows me to have a small error. So this function e, capital E, is small, so converges to 0 when epsilon is going to 0. What I'm doing here now is I'm starting with the differential equation, which is f of t, y prime, y double prime, epsilon. This is a completely generic second order differential equation. Completely generic. Now what I'm saying is that a function y alpha is gonna be a good approximating solution for for my differential equation if this residual error, so if this quantity here, the same function of t y alpha, okay, I wrote here dot, it's prime, y alpha prime, y alpha double prime, epsilon goes to 0 uniformly as epsilon goes to 0. So this, what does this mean? This means that I have the differential equation. The differential equation will have some exact solution. The exact solution is the one that is exactly satisfying the equation. But then I want to understand, can I use an approximated solution instead of the exact one? I can use the approximated solution if this quantity here, so this the residual error, is going to 0 when epsilon goes to 0. Because basically this means that the error between the approximated solution and the exact solution is small. Okay? All right, we have the time for the example. So consider this equation, which is given by y double dot plus y dot squared plus epsilon y equal to 0. Epsilon is much smaller than 1, t is greater than 0, and the initial conditions are y in 0 equal to 0, and y dot in 0 equal to 1. Now let me use the regular perturbation method. So basically, let me write y as a series of y naught plus epsilon y1 plus epsilon squared y2 plus higher order terms. Let me consider an approximation to the first term. So I'm just taking y naught. If I'm taking a y naught, if I'm taking y naught, so if I'm taking the 0 order in epsilon, I will have the following equation. Y dot 0 squared equal to 0. Right? This is the 0 order in epsilon. With initial condition y0 0 equal to 0, y dot 0 0 equal to 1. So I want to solve this problem. How do I solve this problem? Well, for example, I can solve this problem this way. I can set y dot 0 equal to j. So y double dot will be j dot plus y dot squared is j squared. So this is equivalent to this system with y naught 0 equal to 0 and with j in 0 equal to 1. Right? This is the initial conditions. So now what you can do is well, this equation can be integrated by separation of variables. So the second one, I mean, j dot plus j squared equal to 0 can be integrated by separation of variables. Because you can write this as the dj in the t plus j squared equal to 0, which gives dj over minus j squared equal to the t. So if I integrate left and right hand side, what I found is 1 over j equal to t plus some constant kappa, which in turns give j equal to 1 over t plus kappa. But then I'm using the fact that j in 0 is equal to 1, so I'm using the initial condition. And this gives me kappa equal to 1. So j is equal to 1 over t plus 1. That's not the end of the game, because I have to calculate also the first equation, which is y dot 0 equal to j. So y dot 0 equal to 1 over t plus 1. And this gives me a solution which is y naught equal to log of t plus 1 plus kappa. Oops, not kappa, plus kappa tilde. But if I'm using the initial condition y naught in 0 equal to 0, this gives me kappa tilde, kappa tilde equal to 0. So y naught is log of t plus 1. So this would be the approximated solution to the zero order. How good is this approximation? What we have to do is to study the residual error R for this problem. What is the residual error for this problem? The residual error of the problem is the differential equation evaluated in the function that I have assigned. So what I have to do is to take my differential equation that was the original one, this one, right? And evaluate this thing for y not equal to log t plus 1. So I have to evaluate y not double y0 double dot plus y0 dot square plus epsilon y0. Right. How much is this thing, this expression? Very good. That's epsilon y0. Well, y0 is here. It's epsilon log t plus 1. It's epsilon y0 because this thing here is exactly equal to 0. So this y0 is the one that solve this equation here. So y0 double dot plus y0 dot square, this quantity is equal to 0. The only part that survives is epsilon y0. Y0 is log t plus 1, so this is epsilon times log t plus 1. Now, this quantity here is a big O of epsilon, as epsilon goes to 0, for a fixed time t. But pay attention, because this is okay only pointwise, only if you specify the time t. If you do not specify the time t, so if you fix epsilon, I can choose, once that I fix epsilon, I can choose a t which is large as much as I want, and this term would be large as much as I want. So the residual error R would be large as much as I want. What does this mean? This means that this solution is okay pointwise, would be okay for some interval 0t. It's like for the case of the cellular term, would be okay just in one interval. But this is not uniformly a good solution for my problem. It's a good solution only for t included from between 0 and some capital T. But it's not a good solution for all these, for all time. All right. There are just another couple of things for today, which are some kind of problems. Yeah. Any problem? No. Okay. So we have already seen that the regular perturbation method loses validity in many situations, right? We have seen, for example, that we can have problems if we have a solution which is a oscillating solution. We have seen that there are some tricks like the Poincaré-Lindstedt method to eventually evaluate the solution of a problem where I cannot use a regular perturbation method. In order to make crystal clear, in order to perfectamente chiaro, perfectly clear, the fact that sometimes you cannot use regular perturbation method, we will see a couple of examples where this thing is completely spoiled by the calculation. So let me consider the problem given by the following algebraic equation. Epsilon is a positive parameter, much less than 1. So basically this equation is an equation which is the perturbed version of the equation 2x plus 1 equal to 0, which has solution x equal to -1/2, right? Now let me try to use the regular perturbation method to find some approximate solution of this algebraic equation. So I'm looking for a solution in the usual way: x equal to x naught plus epsilon x1 plus epsilon squared x2. I'll stop here. I'm taking this thing and putting into the equation. So I have epsilon times x squared, x naught squared plus epsilon squared x1 squared plus epsilon 4 x2 squared plus 2 x naught epsilon x1 plus 2 x naught epsilon squared x2 plus higher order terms. Then I have 2 that multiplies x naught plus epsilon x1 plus epsilon squared x2 plus higher order term plus 1 equal to 0. Correcto? Correct. Now, zero order in epsilon. Zero order in epsilon is this and this. 2x naught plus 1 equal to 0. First order in epsilon. First order in epsilon is this. So it's x naught squared plus 2x1 equal to 0. Second order in epsilon. This one this one. So it's 2x0 x1 plus 2x2 equal to 0, etc. What are the solutions? This is the solution of the first one is x0 equal to minus 1/2. The solution to the second one is x1 equal to minus 1/8. The solution to the third one is x2 equal to minus 1/16, blah, blah, blah. So what's the solution in total? Solution in total is minus 1/2, minus 1/8 epsilon, minus 1/16 epsilon squared, minus blah, 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 blah. What's wrong with this? So you have this equation. You are looking for a solution with the regular perturbation method. You find this. What is wrong? No. The reason is very easy. Actually. So there is something missing. Look at the equation. What's this equation? What is this? Yeah, it's a quadratic equation. How many roots has an algebraic equation? A quadratic one. 2. How many roots do you have here? Where is the other one? There is no other one. So basically, if you use this method, you cannot find the second root of the equation. This is implicitly telling you that this method is not enough to catch the solution, even approximated solution for your equation. Wait. This basically happens because we didn't think about the fact that the term epsilon x squared can even not be negligible. We are thinking that epsilon x squared is some perturbation, but in principle it could happen that it is not negligible. So what are the possibilities? There are two possibilities actually. What we can do is to study the relative weight of the terms of the equation. So let's see again the equation. What can we see? We can say that, for example, epsilon x squared is more or less like order of magnitude of 1. And then 2x is much smaller than 1. First possibility for this is epsilon x squared. So in order, I'm trying to find a second root. I'm trying to understand where is the second root of this quadratic equation. So let's see what happens if epsilon x squared is of the same order of magnitude of 1 and 2x is much smaller than 1. This is one possibility. The other possibility is that epsilon x squared is of the same order of 2x, and both of them are much larger than 1. Again, the second root is hidden by the fact that epsilon x squared cannot be neglected, non può essere trascurato, cannot be neglected with respect to some other term in the equation. So what I'm supposing here is that either epsilon x squared must be of the same order of magnitude of 1, or epsilon x squared must be of the same order of magnitude of 2x. If I'm speaking too fastly, please tell me, because sometimes I tend to accelerate.
The second one, the second case, so we can't transcribe epsilon square.
With respect to 2x.
Whereas in the first one, we can transcribe 2x.
So basically, okay, the point here is that x squared is multiplied by epsilon, right? So I can think that epsilon x squared is the term to neglect. Transcribe is to neglect. Okay. Let me tell you what happened for the first one, because this probably would give an answer to your question. What happens if epsilon x squared is of the order of magnitude of 1? This basically means that, well, x squared is of the order of magnitude of 1 over epsilon, right? Which basically means that x is of the order of magnitude of 1 over the square root of epsilon. Right? Epsilon is small. Epsilon, it's a very, very small number. So in this case, what does this mean? That x, correct? But in the equation, I was considering 2x to be subleading. So I have here x much larger than 1, here x much smaller than 1, which is impossible, it's inconsistent. Yeah. So this possibility is inconsistent. This choice is inconsistent. I can cancel the first choice. So the second root cannot be hidden in this choice. Let's see this other one. What I have in this other case? In this other case, I have epsilon x squared of the order of 2x. Good. Which basically means epsilon x order 2. Well, order 1, order 2. Which means x order 2 over epsilon. Epsilon is small, so x can be some large number, which is what I have here. So this is consistent. And it is consistent also because I'm looking for a root which is a large root. What I'm saying is that I should have some root which is hidden in the fact that I have some large root that I cannot catch with the regular perturbation method. Okay, so what I can do for finding this root is then to use, you remember, it's something that we have introduced at the very beginning. So basically try to change the variable, the state variable, in order to have something which is of order unity. So what I can do is to define a new variable y, which I define to be x divided by 1 over epsilon. This is basically epsilon x. Now, if I'm considering why I'm doing this? Because epsilon x, what's the order of epsilon times x? Yeah, 2, unity, 1. So yeah. So in this way, I would have some parameter y, which is of order unity, and I can deal with the equations. All right. So what I have to do is to change to transform my equation. What was the equation at the beginning? I don't remember the equation. Epsilon x squared plus 2x plus 1 equal to 0. I have to transform this equation in terms to write it in order to write it in terms of y. And in order to do this, what I can do is multiply everything by epsilon. So it's epsilon squared, epsilon 2x plus epsilon. This thing here is y. This thing here is 2y plus epsilon equal to 0. Sorry, this is y squared. The first term is y squared. Okay. Very good. Now let's do the usual regular perturbation method for this parameter y. So y equal to y0 plus epsilon y1 plus epsilon squared y2. Write down this equation in terms of this thing. What you find is y0 squared plus 2y0 equal to 0. The second, so the equation for the first order in epsilon is 2y0 y1 plus 2y1 plus 1 equal to 0, blah blah blah. Dai, abbiamo finito. So what are the solution of these things? The solution of these things is, the solution of the first one is y naught equal to minus 2. Well, there is also another root, which is y naught equal to 0. But y naught equal to 0 is not possible, because y naught equal to 0 would correspond to x equal to 0. X equal to 0 means that is I'm looking for a root which is very large. So x cannot be x equal to 0, because x equal to 0 of course is not large, right? So this is not possible as a root. The right root for y naught is minus 2. If I'm putting minus 2 here in the second equation, I find y1 equal to 1 half. Blah blah blah. Other terms if I'm going down and down. So what is the solution for this ansatz, for this regular ansatz? This would be minus 2 plus epsilon 1 half plus other terms. But now what I have to do is to transform back to x. I need my root in x. You remember, y is equal to epsilon x. So x is equal to y divided by epsilon. So from here, what I found is x equal to minus 2 over epsilon plus 1/2 plus higher order terms. That's why actually with the regular perturbation method you couldn't catch this solution. This solution here is very large solution when epsilon is going to 0, because there is this term here. So what's the lesson here? The lesson here is that even when you are considering algebraic equations, when you're considering quadratic equations, when you have terms that you are considering to be subleading, you must be very careful, because these terms could not be so subleading, like in this case. So if you are considering, if you are trying to solve the problem with the regular perturbation method, you could easily lose this on the road some of the solutions, some of the rules, some of the solutions. This happens for algebraic equations. This happens for differential order equations, and so forth and so on. Well, this specific case is for algebraic equations. Okay. 43, guys. You are tired. Ooh, I am tired. So let's stop here for today. Handwritten notes online tomorrow afternoon, and that's all. Thank you very much. Thank you guys there at home as well. Grazie a voi.
Thank you, Professor. Bye.
Thanks.
Thank you.
Thank you, Professor. Bye.
Thanks. Cheers.